Okay, I want you to picture a scenario. It's Tuesday morning, you've got your lukewarm coffee, and you open a file.
Right.
And you're expecting to find an answer. Maybe it's sales data, survey results, something from a server log. But instead of an answer, you just get hit with what I call the wall of text.
Oh, the dreaded matrix.
Exactly. Just rows and columns of numbers, scrolling down into infinity. It's almost physically painful.
It is.
You start scanning it, looking for a high number, maybe a low number, but after 30 seconds, your eyes just glaze over. It's table fatigue.
It's a very real biological phenomenon. Our brains are incredible pattern recognition machines, but we are absolutely terrible at processing raw matrices of numbers.
It just didn't evolve to read spreadsheets.
Not at all. And when you stare at a table, you get overwhelmed by the individual points, and you completely miss the structural reality of what's happening.
And that is the problem we are solving today. We're doing a deep dive into graphical data exploration in R. We have a stack of material here, specifically digging into Chapter 2 of a pretty dense technical guide on using the R programming language. But the mission isn't just about learning code.
No, the mission is to understand how we turn that chaos of numbers into a story.
Right. And I want to be clear, we aren't just talking about making things pretty. This
Yeah.
isn't about slapping a 3D pie chart into a PowerPoint to keep your boss happy.
Please never use 3D pie charts.
Duly noted. But seriously, this source material, it treats visualization as a diagnostic tool.
Yes, that's the key.
It's about using R to interrogate the data, to catch errors, and to reveal patterns that the raw numbers are actively hiding from you.
Exactly. We're going to look at everything from basic histograms to some really advanced stuff, things called trellis graphics.
And we're going to use a really fun playground for this, which is linguistics.
Yeah, the dataset examples are all about how humans use language, word, frequency, reaction times, sentence structure.
Which I love because language data is notoriously messy. It's just full of exceptions and weirdness.
Precisely. And if you can visualize the chaos of human language, you can visualize anything.
So let's unpack this. Before we can even draw a single pixel, the text makes a huge point about defining your terms. Specifically, the difference between a constant and a random variable. Now, to me, a variable is just something that changes. But in stats, it's a bit more nuanced.
Is the bedrock of the entire field. A constant is just. It's a fixed value.
Okay.
The source uses the example of the Brown corpus, that famous collection of text from the 1960s.
Right.
If you write a script in R to count the words of the Brown corpus, you will get the exact same number today, tomorrow, and 10 years from now. It's a fact.
Got it. It's static.
But a random variable is the outcome of an experiment. You know what the possible outcomes are, but you don't know which one will happen, right now.
Like flipping a coin. I know it's heads or tails, but I don't know which one until it lands.
Exactly.
Yeah.
But let's apply that to the linguistic data we're looking at. Take familiarity ratings. If I ask you to rate the word gherkin on a scale of 1 to 7, your answer is a random variable.
Because it varies from person to person. Or even if you ask me twice, I might change my mind.
That's it. So statistics is really just the game of trying to find the rules that govern those random variables.
We're trying to map the probability distribution.
Precisely. What's likely, what's where. And you cannot see that distribution by staring at a spreadsheet row by row. You have to visualize the shape of it.
Which brings us to the first look. So the text talks about visualizing a single variable, and they immediately draw a battle line between two charts that look identical to the untrained eye.
The bar plot and the histogram.
Yes, they look similar, but you're saying using them interchangeably is a cardinal sin in data science.
Oh, absolutely.
I feel like I sin many times then. Break it down for me.
Well, it comes down to the type of data. A bar plot is for discrete variables.
Discrete, so things you can count.
Exactly. The source uses the ratings data set, looking at word length. A word has 3 letters, or 4 letters, or 5. It cannot have 4.5 letters.
Right. There's no continuum. You're either in the 4-letter bucket or the 5-letter bucket.
So you use a bar plot. The bars are separate entities. And in this data set, you can instantly see the mode. The most frequent value was 5 letters. It's just a simple count.
Okay, but a histogram is for continuous data, right? Like time or
Yeah.
height?
Yes. Data that can be measured with, infinite precision. But the text highlights a very specific technical detail about histograms in R. Specifically, using the truest function from the mass_s package.
And before you explain that, can we just touch on the mass_s package thing? The source makes a big deal about loading the library. Why isn't this stuff just built in?
Well, that's actually the beauty of R. It's designed for memory efficiency.
Okay.
Think of R like a master carpenter's workshop. You don't dump every single tool you own onto the workbench before you start.
You'd have no room to move.
Right. You keep the basics out: hammer, tape measure. But if you need a specific high-precision laser level...
You go to the cabinet and get it.
Exactly.
Yeah.
Mass is the cabinet. TrueHist is the laser level. You have to tell R, go get this library, so it doesn't clog up your computer's memory with tools you aren't using.
Okay, so we've gone to the cabinet, we've loaded mass, and we run TrueHist. How is this different from my sinful old bar chart?
It's the vertical axis. This is the aha moment.
Yeah.
In a standard bar chart, the height is just the count. There are 50 words here.
Right.
In a proper histogram, the area of the bars is scaled.
Scaled how?
So that the total area of all the bars combined equals 1.
1, as in 100%.
Yes, it represents the total probability space. And this transforms the image from just a count into a mathematical statement.
So you can look at the bars for word lengths 5 and 6 and visually add up their area?
And say, these 2 bars account for 40% of the total probability. It lets you make statistical claims just by looking at the graph.
That is cool. It's like the graph is doing the math for you.
Yeah.
But the text also points out that histograms have a flaw. They're blocky.
They're jumpy.
The bin width problem.
Right. A histogram groups data into these bins. But how wide do you make the bin? If you make it too wide, you lose all the detail. It just looks like one big block.
And if you make it too narrow, every single data point gets its own tiny tower, and it looks like static.
And the scary part is, depending on where you set that dial, the shape of the graph actually changes. You can accidentally hide a pattern just by choosing the wrong bin width.
And nature doesn't usually work in square blocks.
No, it works in curves.
Enter the density plot.
The density function. Imagine taking that blocky stepped histogram and draping a wet silk sheet over it.
I love that image.
It smooths out the hard edges. It calculates a continuous line that flows over the peaks and valleys of the data. And when they apply this to the Lexic data set...
Which is reaction time.
Right, reaction time, so something really important happens.
The shape appears, and it is distinctively not a bell curve.
It is not.
Yeah.
We are so trained to expect that normal distribution, that perfect symmetrical bell. But reaction time data is skewed.
It has a long right tail.
Think about what that means physically. If I measure how fast you can hit a button, there's a biological floor. You can't react in 0 millisecond.
Your nerves need time to fire.
Right. So there's a hard wall on the left side of the graph. I can only be so fast.
Exactly. But the other direction, how slow can you be?
I mean, I could zone out. I could sneeze. I could go make a sandwich.
Precisely. There is no ceiling on slowness. So the data piles up against that fast wall and then trails off into this long, thin tail of slower responses on the right. And this creates a huge problem for statistics, doesn't it?
A huge problem. Most basic statistical tests, they assume symmetry. If you feed them this skewed long-tailed data, they will give you the wrong answer.
So the average gets pulled way over to the right by those few slow people.
Yeah. So the visualization diagnosed the disease, what's the cure? The source material suggests something that sounds like cheating, but apparently isn't.
The logarithmic transformation.
It feels like magic, but it's just math. You just apply a log function to the reaction times.
But explain to me why that works. Why does logging the numbers fix the shape?
Well, think about how a logarithm works. It shrinks large numbers way more than it shrinks small numbers.
Yeah.
So it takes that long, stretched out tail of slow reaction times, and it reels it in. It compresses the distance on the right side of the graph.
So it's like a funhouse mirror that corrects the distortion.
That's a great way to put it. And the source shows this using box plots.
Right, the little rectangles with whiskers.
So the box plot of the raw data, it looks broken. It's this squashed little box with a comet tail of outliers flying off the top. It looks messy, unmanageable.
But the box plot of the log reaction times.
It's symmetrical. The outliers are pulled in. The box is centered. It looks like a proper normal distribution.
So by transforming the data, we make it fit the tools that we have.
And this is the key takeaway here. You visualize to find out if your data is broken. If you had just run a t-test on the raw numbers, you would have been wrong. You had to see the skew to know you needed the log transform.
Okay, so we've mastered the single variable. Now let's talk relationships. Two variables dancing together, the classic scatter plot.
The plot function. This is the bread and butter of science. Does X cause Y?
The text uses a really interesting linguistic question here. Do words that appear frequently have more family members?
And by family, we mean morphological family size.
All right.
So you take the word work, Its family includes worker, working, artwork, homework.
Got it. So if a word is popular, does it get used as a building block for other words?
That's the hypothesis. So they plot frequency on the x-axis and family size on the y-axis.
And generally, yeah. The cloud of points drifts upward. Common words have big families, but cloud is messy. And here the text uses a word that I absolutely love.
I think I know which one.
Heteroskedasticity.
It is a wonderful mouthful.
What does it actually mean?
It refers to the shape of the noise. In an ideal world, the scatter of points around the trend line would be constant, like a nice uniform tube of data.
But here the cloud is shaped like a megaphone.
A megaphone, exactly. It starts tight and gets wide.
So at the low frequency end, there's a ton of variation, lots of noise. At the high frequency end, the pattern is tighter.
And that uneven variance is heteroskedasticity. It makes it very hard for your naked eye to judge where the true center of the trend is.
Because my eye gets distracted by all the noise at the wide end of the megaphone.
Correct. So we need a tool to cut through that noise. The text introduces the smoother,
The lowest function.
locally weighted scatterplot smoothing.
Rolls right off to tongue.
It does. Imagine a little window sliding across your graph from left to right. As it moves, it calculates the average of just the points inside that window.
So it's finding the local center of gravity.
Yes. It draws a line through the chaos. And when they ran this lowest line, it revealed something the scatterplot hid.
That the relationship wasn't a straight line.
No, it was curved. For low-frequency words, the line was basically flat. Family size didn't change much.
But it only started shooting up once the words hit a certain threshold of popularity.
Which is a massive insight. If you had just run a simple correlation calculation, it would have given you a single number, maybe 0.5. It would have lied and told you it was a straight line.
The visual smoother told the truth. I feel like "The Average is a Liar" should be the subtitle of this deep dive.
It often is.
Okay, let's pivot to categorical data. We've been talking about numbers time, frequency. What about categories like yes, no, non-verb?
Right. You can't do a scatter plot of that. Typically, people use stacked bar charts, but the source makes a strong case for the mosaic plot.
I hadn't used these before. It looks like a tiled floor where all the tiles are different sizes.
That's a good way to describe it. The mosaic plot function, it represents a table of counts using rectangles. And the crucial thing is that the area of the rectangle is proportional to the count.
They apply this to the date of alternation data set.
Which sounds fancy.
It does, but it's just about how we say things, like I gave the book to him or I gave him the book.
Right. Prepositional phrase, to him, or noun phrase, him. And they wanted to see how this interacts with animacy. Is the receiver alive? And givenness.
Have we mentioned this person before in the conversation?
Exactly. And the mosaic plot showed this really clearly.
A massive asymmetry.
Huge. The boxes for given recipients, people we already know about, were huge and almost entirely noun phrases. I gave him the book.
The visual weight of the box just made the pattern pop out.
Yes. It shows we prefer to put old news early in the sentence. And seeing those big blocks of area makes that intuitive in a way a table of percentages never could.
Okay, we have arrived at the heavy hitter, the final boss of this chapter, trellis graphics.
Named after the garden trellis, because it's a grid.
The idea here is that sometimes looking at all the data together just hides the real story. You need to slice it. You need to condition the data.
It's divide and conquer. You want to see the relationship between X and Y, but you suspect that relationship works differently for Group A than for Group B.
The example they used was incredible. It brings us back to reaction times, comparing native speakers to non-native speakers.
Yeah, they used the lattice package for this. They created a box plot, but they split it into panels. Panel 1, native speakers. Panel 2, non-native speakers.
And the first step was obvious. The non-native box was higher up the graph. They were slower. No surprise there.
Learning a language is hard, yeah. But then they split it again. Within those panels, they separated correct answers from incorrect answers. And this is where the human insight was hiding.
This part blew my mind. For the native speakers, the incorrect answers were faster than the correct ones.
Think about that. When a native speaker gets it wrong, why? It's because they rushed. They clicked before they processed.
It's a fast and wrong error. I do that all the time.
We all do. But the non-natives...
The complete opposite. Their incorrect answers were slower.
So they stared at the screen, hesitated, second-guessed themselves, and then got it wrong.
Slow and wrong.
The cognitive mechanism of the error is completely different. One is a slip-up, the other is a processing failure.
And here is the kicker. If you had just averaged everyone together,
You would have seen zero difference. The fast errors and the slow errors would have canceled each other out,
And you would have concluded error speed is the same as correct speed.
which is just flat out wrong.
Yo,
And
sure.
it demonstrates why you have to condition the data. You have to peel the onion. If you don't use trellis graphics to split these groups apart, you miss the actual human story.
They took this one step further with something called shingles, which sounds like we're roofing a house.
It's a similar concept to overlapping tiles. This is for when you want to split the data, but you don't have clear groups like native versus non-native. You have a continuous number like frequency.
So you have to create artificial groups.
You create bands. Band 1 is low-frequency words. Band 2 is medium-low, and so on. But they overlap slightly, like shingles on a roof.
And when they plotted the relationship between family size and complexity for each shingle, they found what statisticians call an interaction.
The relationship wasn't universal. For the low-frequency shingle, the line was flat. No relationship.
Yeah.
But as you move to the high-frequency shingles, the line started to point up.
So the relationship only turns on for common words.
Exactly. The effect of one variable depends on the value of another. It's a nuance you would miss 100% of the time if you just ran a global correlation.
It really reinforces this idea that visualization is an interrogation.
It is. You're
Yeah.
checking your assumptions. Is it normal?
Hmm.
Plot it. Is it linear? Smooth it. Is the same for everyone. Trellis it.
I want to leave our listeners with one final thought from the source material because it was honestly kind of eerie. It's an exercise involving Moby Dick.
Zipf's law. This is one of the most famous and frankly mysterious findings in linguistics.
So the text suggests taking every single word in Moby Dick, over 200,000 words. You sort them by frequency. The is number 1, of is number 2, all the way down.
You rank them.
Then you take the logarithm of the frequency and the logarithm of the rank, and you plot them against each other on a scatterplot. What do you see?
You see a perfect straight line. Specifically, a line with a slope of -1.
That is just weird.
It is profound. It implies that the second most common word is exactly half as frequent as the first, the third is 1/3 as frequent, and so on.
But Moby Dick is a creative work. It's messy, it's emotional, it's human art, and underneath it, there's this rigid mathematical skeleton.
And it's not just Moby Dick. It's basically every language on Earth, whether it's English, Mandarin, or, the text of this very conversation.
So there's a hidden efficiency principle in the human brain.
A mathematical law governing how we think and speak that we aren't even aware of
And the only way to see that hidden law
is to find the right way to visualize it.
Yep.
If you look at the table, it's just noise. If you plot the logs, it's a law of nature.
So the next time you open a spreadsheet and feel that table fatigue setting in, just remember, there might be a straight line hiding in that chaos. You just need the right tools to drag it out into the light. Thanks for diving in with us.
Always a pleasure.
See you next time.